Have you ever stopped to think about all the invisible forces at work that just keep things stable? Well, today we're pulling back the curtain on one of chemistry's true unsung heroes, the buffer solution. These are the silent guardians that maintain balance in literally everything, from the medicines we take to the very blood pumping through our veins. So let's start with a question that's pretty important for all of us. What is it that stops our body from going completely haywire every time we drink a lemonade or eat a tomato? What's standing guard?
It all comes down to this number, 7.4. That is the incredibly precise, super delicate pH of healthy human blood. And that's not just a suggestion, it's pretty much a non-negotiable set point for being alive. And when I say precise, I really mean it. Our bodies can only handle the tiniest little wiggle room from about 7.35 to 7.45. If your blood's pH were to drop below 6.9 or shoot up past 7.9, that's a change of less than one single point. It becomes catastrophic. We're talking about an incredibly razor-thin margin for error.
So that's the massive challenge, right? How in the world do we maintain this delicate balance? And this isn't just about our bodies. Countless things, from industrial processes to sensitive lab experiments, totally depend on keeping pH locked in and stable. And that, my friends, brings us to the hero of our story. The solution to this whole problem is the buffer. It's time to meet our pH guardian. So what is a buffer solution? Well, think of it like a chemical shock absorber. Its entire purpose in life is to take a hit. You can splash in a little bit of a strong acid or add a bit of a strong base, and the pH just shrugs it off. It barely moves. It's like a bodyguard for pH. Now, that sounds like some kind of magic, but it's all just incredibly clever chemistry. So how do they pull it off? Let's pop the hood and see what these amazing solutions are actually made of. And here's the secret sauce. It's a surprisingly simple recipe. You've basically got two flavors. For an acidic buffer, you take a weak acid and you pair it with its other half, what we call its conjugate base, which is usually just a salt. And for a basic buffer, you guessed it, same idea. A weak base gets paired up with its conjugate acid, also a salt. It's this partnership, this dynamic duo, that gives them their superpower. To make this a little more real, think about vinegar. It's mostly acetic acid, a weak acid. If you mix that with its salt partner, sodium acetate, boom! You've just made a classic acidic buffer. On the flip side, if you take a weak base, like ammonium hydroxide, and mix it with its salt, ammonium chloride, you get a common basic buffer that you might find in something like a cleaning product. Okay, so we know the ingredients now, but how do scientists get that recipe perfectly right to hit a super specific pH, like that 7.4 we need for our blood? I mean, this is the exact puzzle that chemists in research labs and drug companies have to solve every single day. How do you go from just knowing the ingredients to creating a solution with the exact pH you need for your work?
Well, the big secret isn't some fancy, complicated chemical you have to add. It's all about the ratio. It's just about controlling how much of the salt you have compared to how much of the weak acid or base you have. That's it. By tweaking that ratio, you can dial in the pH with incredible precision.
And this right here, this is the master recipe they use. It's called the Henderson-Hasselbalch equation. Now, I know it might look a little intimidating with the log and the brackets, but don't let it fool you. All this is a super powerful and practical tool that lets chemists design the perfect buffer every single time.
What's so cool about this equation is that it's a two-way street. If you've got a buffer solution already made, you can plug in the amounts of your ingredients and calculate exactly what its pH is. But even better, if you know the pH you want, the formula tells you the exact ratio of salt to acid you need to mix together to get there. It's fantastic. All right, so we have the formula to get the ratio just right, but that brings up another question. How do we even pick our starting ingredients? You can't just grab any weak acid off the shelf and expect it to work. So let's see how chemists pick the right team for the job. The absolute key to choosing the right buffer system is a value called the pKa. You can think of it as a number that tells you the acid's personality or its inherent strength. A buffer is at its absolute best. It has the most power to resist change when the pH you're aiming for is super close to the pKa of the weak acid you're using. And that leads to this amazing little rule of thumb that chemists use all the time. When you need to make a buffer, you just look for a weak acid whose pKa value is within 1 pH unit of your target, so plus or minus 1. This instantly helps you zero in on the perfect candidate.
Check this out. This chart shows you exactly how that works in the real world. So let's imagine you need to run an experiment and hold the pH steady at, say, 7.2. You just scan down this list, and bam! There's the phosphate buffer system with a pKa of 7.21. That's a perfect match. That's your guy. Need to work around pH 9? Looks like the ammonia system is the way to go. It's that simple.
So it turns out these systems are just constantly at work all around us. They're keeping our blood stable, they're making sure medicines work properly, they're critical for countless lab experiments. They're these invisible, essential guardians maintaining the chemical balance that our entire world really depends on. And that kinda leaves you wondering, doesn't it? Buffers are just one example of these elegant, hidden systems that keep everything from flying off the rails. What other invisible chemical processes are out there, silently working to keep our world in balance?